Thank you very much and welcome to this presentation. My name is Lainey Gutierrez-Ferwick. I'm a professor of biomechanics at KTH in Stockholm. I would like to acknowledge my collaborators on this project. This project falls under the Digital Futures project typed Societal Innovations project, with a specific theme for digital tools for remote rehabilitation. It's a 1 to 2 year project begun just before last summer. The general goals of this project deal with remote rehabilitation, which currently lacks a certain amount of, let's say, quantitative and longitudinal follow-up ability. So with this project, the aims were to design a tool that attacks those problems, just as I said, and at the same time promoting live interaction and feedback between the treating clinician and a patient. And we are focusing on physical health, physical therapy, so the musculoskeletal system. During the past 5 years or so, there's been great developments in using 2D videos, for instance, smartphone videos, combined with deep learning-based methods such as open pose and alpha pose for pose estimation. And these methods can have a lot of great advantages, for instance, in tracking several subjects at the same time. However, they are 2D estimations. There's also been some work in using several devices to estimate 3D motion. However, for certain applications, this may or may not be accurate enough. In, let's say, a medical setting or a clinical setting, I think there's good reason to question the accuracy of these, as well as the feasibility of someone at home in their kitchen using 2 synced devices. Since 2020, iOS models have included a LiDAR sensor, which is used to scan a 3D topology in real time. You can see on the top right there an image of what the LiDAR sensor is doing. It's sending out a strobe of a grid of lights and recording the backscatter of each of these ones, and thereby creating this topology of everything in the view field in real time. And Apple also has a great advantage of its built-in AR kit, which from this scanned 3D topology can identify a human subject and fit it to a model, which you can also see imaged there. So this is something more than 2D. I don't know that I would quite say it's 3D. I've heard the expression 2.5D, which I think applies relatively well here. So this has been studied to a limited amount in accuracy in estimating human motion, and it's been reported to underestimate range of motion. So this is a short demonstration of how the technology can work. This is my colleague who let me film her recently at a conference, and you can see that the AR kit is instantly fitting an avatar over her, and using an app that I downloaded called MobileCap, we can estimate the motion of different joints of her body. So naturally, we were interested in measuring the accuracy of the AR kit to measure human motion. So we did some data collections in our fully equipped 3D motion capture lab. So here is a test subject who happens to look a lot like me, both equipped with markers for 3D motion capture and then simultaneous data collection with, in this case, an iPad Pro. And I tried to do some isolated motions, for instance, only flex and extend my left knee or my right hip and so on. And here you can see some of the early preliminary results from both the raw AR kit output and from the 3D motion capture, which we can call, let's say, true in this case. So this was kind of promising and yet flawed. So to perform a more systematic analysis and to construct a neural network, we invited 10 able-bodied subjects to again come to our lab and for simultaneous data collection in both our 3D motion capture system and with, in this case, 2 iPad Pros from 2020. We asked them to walk on a treadmill for about 5 minutes each, and then we were able to collect several hundred gait cycles per person. We focused only on the lower limbs in this case. We computed the lower limb joint angles from both the 3D motion capture system and from the AR kit. A artificial neural network was constructed, and it was trained to map the AR kit's features, let's call that the raw AR kit, to the 3D, let's say the true joint angles from our motion capture system. And these trained angles are called refined. So data from 8 subjects was split 9-to-1, training testing for the intra-subject analysis, and 2 subjects' data were withheld and used for inter-subject analysis. An agreement or accuracy of both the raw AR kit and the refined angles are described as root mean squared error and correlation between the 3D motion capture system and these two. So here I'm illustrating just a little bit of the results here. On the left side you can see the hip angle, and on the right side the knee angle. And for each hip angle, let's see, when it's about the highest, it's the start of a gait cycle, and then it ends again at the peak again. So that's about 3 gait cycles. And you can see 3 different curves here. The raw AR kit is shown in that blue dotted line. The 3D motion capture is shown in black, and the refined angles shown in orange. And you have some analyses of the accuracy between the different models. So in the intra-subject tests, the AR kit untrained had actually quite high error, root mean squared error, and a medium to good correlation. But when trained, the root mean squared error of the angles was 3 to 4 degrees on average, and very, very high correlation coefficients. In the inter-subject tests, I'll just skip down to the trained one. Again, we were able to achieve accuracy or agreement of these angles to between 3 and 6 degrees, and again, high correlation. So what does this tell us, and where are we now? Well, I can conclude that the raw AR kit itself can do some pose estimation, but it's too inaccurate for any kind of a clinical application. The AR kit was able to estimate hip motion somewhat better than knee motion, although the range of motion, the extreme flexion or extreme extension, were underestimated. The ankle angle was very, very poorly estimated, and I didn't even include it in this analysis. However, when this AR kit output was adjusted with the neural network, trained with the 3D motion capture data, it was much more accurate, both in intra and inter-subject models, which is quite promising. I do want to point out, however, that applications for expectation must align with camera resolution. Earlier in the presentation, I had an image of the strobe dots on a subject. As of now, 2022, the resolution has not improved, not even on the newer models. So that's an important thing to remember moving forward. Having done this, I think we actually need to change our approach on machine learning. So we've been working for the past few months on, instead of training the joint angles, training the joint centers, so replacing the joint centers and then recomputing the joint angles. At the moment, our data is a little too preliminary for me to have any results for you. The way I envision this working, and I do envision this working, is that we probably need to train a neural network for each subject, as I believe each person's topology and that relationship to their joint centers is going to be rather individual. The way I see this working is we could bring a person into a lab and train a neural network for that person, and then use it for follow-up for, say, a few weeks or months during a rehab period. We are planning some pilot tests on persons with gait deviations, and we're going to compute all kinds of clinically relevant statistics to know not just statistical accuracy, but clinical and realistic accuracy. We're doing some more tests to investigate optimal placement of these iPads and different situations, clothing, for instance. And then we're continuing to work on the app. So with that, I thank you for your attention and I welcome any questions.